and I'm going to talk about some spectroscopic observations in a lot of different wavelengths. Basically, it's my SPD talk, so I'm sorry to people who have attended that. But so eclipse observations, we know the moon is the best accounter, and there are a couple of spectral lines in the visible and a lot more in the near infrared, as Jenna might do for the 2024 solar eclipse. So here I just show you an image, composite image of the white light on the green line from iron 14 and the red line from the iron 10. And as you can see there, eclipse provides, as the moon is the best accounter, it provides a good opportunity for us to measure the off-ring corona structures. For the east link that we'll be focusing on in the rest of my talk, we can see the corona hole. There is an active region on the disk, and you can see those field lines here. And towards the northeast, you can see kind of a superposition of the cusp-like structures and some open plume-like structures, which is actually from a low-altitude corona hole at the far side. And you can also see the streamer structures dominating the equatorial regions. Doing spectroscopy means we can measure more properties like the Doppler shift, the line widths, which are kind of critical parameters that we want to measure to answer the questions about corona heating and solar wind acceleration. And doing spectroscopy in visible, we're doing forbidden lines. They're affected by the photoexcitation and resonance scattering. And we can make spectrograph with smaller instrumental widths, which is optimized for measuring the line widths. And we want to combine some observations for UV and chronograph, which is COM actually. So a little bit more about the line broadening. And I think most people are familiar with this here, so I will just skip. Basically, we have two terms. One is what we call the thermal broadening, which is related with the thermal motions of the particles in the hot solar corona. And we have another ad hoc term, I would say, the non-thermal broadening, which is everything beyond the thermal broadening. It might be wave-driven, but it's hard to say. So in the rest of my talk, I will use effective velocity both effective velocity or effective temperature to represent total line width. I think the definition of the effective velocity here is the same as the 1/E velocity used by COM. So we're on the same page.
That's a quick question.
Yeah.
Did you include instrumental broadening at that epsilon, or did you take that out first?
I will remove instrumental broadening when I do the data reduction. Those for COM and for the spectrograph that I'll introduce later. So this is Shadia's spectrograph. She and Addy didn't develop this instrument. It's a dual channel spectrograph, kind of optimized for observing the green line and red line. It works at really high orders, above 50s, and we have a decent spectral resolution at those wavelengths. And so the strategy of the observation they made in 2017 is they disable the track motion of the telescope during the totality so that the slit, or actually the sun, slowly dripped across the slit. And the camera made intermittent exposures. So every gray stripe you see here is a single exposure, and the typical exposure time is 1 second or 3 seconds. So the camera or the spectrograph is making observations of the off-ring spectrum during the eclipse along those stripes. Yep.
How did they select that part to observe? Why not the emissions from the?
I think they just put the slit kind of around the meridian, and they just let it happen.
2017, right?
Yeah, 2017.
I think they actually did this on both sides, maybe.
Yeah.
There was the focus issue on that side. I'm trying to remember.
It seems that there's some issues with the data at the west link, I guess, so they just give me the east link data. Yeah. And I show some example spectrums from some positions of the slit. You can see it's a multi-order spectrograph. So you can see the iron 14 line appear several times across the detector. So for this study, we only analyzed the strongest order. And we're trying to look for some ice observations because we want to combine some UV spectroscopy. Unfortunately, ice does not make any simultaneous observations during the eclipse. So actually, those two field of views, the Quaison observation was taken about 3 hours after the eclipse, and the corona hole observation was taken about 4 or 5 hours before the total solar eclipse. And we have combo observations during the total solar eclipse. So we have 3 really different field of views of these instruments, but I will try to make some comparisons between them. So what kind of spectra that can we collect from maybe 1 second or 3 second exposures? So here I show you the offlink, which is kind of the light intensity to the continuum ratio of the iron 14 and iron 10. There are some data gaps that I show here, but in this plot, I just fill them with interpolation. But as you can see, there's a active region at close to the link, and so we can collect spectra from the kind of the north region where the cusp and the open fields overlap, and absolutely the bright active region, and also the streamer the streamer structures. And in iron 10, we can measure the spectral lines in the corona holes, also in the active region. You can see there are some cool materials from the active regions between the gaps in the iron 14 and also from the Quaison regions below the streamer. So a little bit more look into our data. So on the top panel is the narrowband imager of the iron 14, and here I compared it with the intensity to continuum ratio measured by the spectrograph, so they're kind of co-aligned with each other. So if we look at the Doppler velocity, we can see there's a large redshift region in the the northeast part, where the open field and closed field kind of interact with each other. But in the rest of the field of view, we don't see large Doppler shift. And for the line widths, the most obvious pattern we see is that near the equatorial region, we observe close to the active region and the streamer, we found very narrow spectral lines. The effective temperature is only 2 to 3 million Kelvin. But for the higher altitude streamer regions, we found broader line width. So we can also make put a few manual slit and to kind of measure the variation of the line width with height. So in this kind of thing, the streamer region, in the northern streamer region, we see the effective temperature about 30 to 40 kilometers per second. Doesn't show a very clear variation versus height. In the active region, we found a typical line width of 30 kilometers per second, and it also doesn't show some significant variation. And yep.
On your previous slide,
yep,
you had in the active region,
yep,
you have a lot of structures adding up on your line of sight.
oh,
So it's going to integrate through structures that are oriented differently. How is that going to impact things like the Doppler? Because it's going to wash some things out. In an active region, you have motion. So how much of that do you think is washed out versus in the more coherent large scale structures?
I think that's an interesting question because we found that the total line widths we measured here are kind of similar with some ice observation. They say they only take trace one corona loop in the active, close to the active region. And we found the line widths are actually similar. I mean, though we have a much poor spatial resolution compared with ice, but it seems that the line of sight integration doesn't play an important role here. But yeah.
I'm curious why the effective temperature was larger in the larger scale structures, because those are both closed regions.
Yeah, but I think for those regions, it's kind of at the boundary between the closed and open field structures because they're kind of at the edge of those streamers. So I would say there might be overlap of both open and closed field structures along the line of sight at the boundary of those regions, which kind of increase the line width a little bit, I will say. But I will show later that we found the patterns in the open field and closed field are the line widths in the open field and closed field are pretty different. In the open fields, usually you would expect larger total line widths.
Okay.
Yeah.
Yeah, and the Doppler too, it's lower than the active region. That's
Yeah.
why I thought it was a line of sight. Mixing, washing out. Structures along the line of sight.
I mean, I've seen something similar in simulations that in active regions you have less mass velocity along the line of sight if you integrate it up and also line of sight.
In
velocity.
individual structures, you can resolve in your model. It's still
Yeah, I mean, we can look more carefully, but I got the same impression.
interesting.
At least in general terms, it's similar.
Okay, thank you.
So basically take some manual cuts and so for both the kind of two closed regions, I mean the northern streamer and the active two cuts in the active region, we found the line width is kind of constant with height. At the edge of the southern streamer, we kind of see some increase of the line width between 1.02 to 1.03 solar radii. But above that, the noise, the data were really noisy, and it's really hard to tell if we do see a plateau of the line width or the line width starts to decrease. And so it seems that we kind of have some very different patterns of the line width variation in the closed fields and open fields. In the closed fields, the line width, the lines appears to be narrower and we show less variation. But in the open fields, we found broader lines and sometimes they do increase with height in iron 14. For the iron 10, we do similar things. This is a comparison between the iron 11 and iron 10. Sorry, we don't have a iron 10 narrow band imager. So basically, we also kind of co-align them. And there's no significant Doppler shift that we found in the iron 10. And for the line widths, similarly in those closed field regions like the active region and the quiet zone regions below the streamer, we found narrower lines. But in the corona host, everybody knows the lines are really broad. And if you calculate the effective temperature is 4 to 8 million degrees, which means there should be some significant non-thermal broadening or preferential heating of these ions. So if we do similar thing, measure the variation of the line width versus height in the active region, the total line width slightly increases between 1.0 to 1.03. And in the corona hole, as you can see along this green corona hole cut, the line width increases significantly between 1.0 to 1.3 solar radii. Maybe we found a plateau, but above 1.3, the noises are huge, so it's hard to tell. But it's interesting that when we look at this cut just along the region where the open fields and closed fields overlapped, in the line of sight, we found close to the link, the line widths are smaller, which are more close to the quiet zone values, while the line width kind of increases drastically between 1.01 and 1.02 solar radii and makes the value more closer to the open fields value. So it seems that the line of sight integration really play a role here, that close to the link, you are observing some closed field plasma, while at larger height, you observe some plasma in the open fields. So the line widths kind of show two different patterns at different heights. So similarly, we found these patterns in the closed fields. We found narrow and those lines slightly increases. But for the open fields, we found the lines are really broad and they increases with height. And then let's go to the comp observations here. So this is the comp observations during eclipse at the east limb. To make a comparison with the spectrograph, I rebinned the comp observations and I made a 2D plot, 2D histogram for the comparison between the Doppler shift and the line widths. So basically in the Doppler shift, we found the similar huge redshift in the northern streamer regions, which is consistent. In the other regions, we don't find significant Doppler shift in both, I would say, COMP and PARMIS, which is the spectrograph data. And it's kind of within the uncertainty of the absolute wavelength calibration of the spectrograph. And for the line widths, we also found some consistency between the COMP and the PARMIS data. Near the equator, close to the active region and streamers, the lines appear to be narrower, while at the edge of these streamers, the lines appear to be broader.
Ask a
Yeah.
question, and sorry, you may have just said this or I missed it, but you did something to subtract out the rotation of the sun?
Here, I just use it. So for both the spectrograph and COM data, I just use a simple way just to subtract the median value of the entire field of view. Yeah. So maybe I should do in a better way, maybe to fit the rotation at each latitude. Maybe I'm not sure if that's a little bit better.
Yeah, that's something we can talk about.
Yeah.
Or we could just comparing the two instruments are both got the same
But
rotation.
that's the
so
point that I
shouldn't really
missed, so it
matter.
doesn't really matter in terms of the comparison.
Yeah.
Yeah, but in terms of interpretation, it matters, I suppose.
Yeah.
And have you removed the instrumental line width at this
Yeah,
point?
I have removed the, I also use the 21 kilometers per second.
You did, okay.
Yeah.
And you removed the median of COMP from COMP and the median of PARMIS from PARMIS.
Yeah.
Yeah.
In context already the median removed as well as you, so this is our definition of how we define the rest one is basically taking this across the field of view, maybe not the entire field of view, but.
Yeah, I only do for the.
You can only do for your
Yeah, my field.
yeah, which I think is perfectly consistent with Eclipse, so.
It's interesting, the effective temperature from COMP, which is a slightly cooler line, is higher. Am I reading this
Yeah.
correctly?
Iron 13 and 14 are not very different. I think the maximum formation temperature is about 1.6 million to 1.8 to 2 million, I guess. So they're not that different, I would
But,
say.
When you see effective temperature, it's not a real temperature, right? It's the
It's the width,
of the
it's the
line.
width of
Yeah.
the line, yeah. I'm just trying to think, that's why I was asking about the instrumental line width. Still trying to figure out why it's higher in COMP systematically.
Yeah, I think they're not that different. I mean, there are both uncertainty, I guess, for comp instrumental width and instrumental width that we determine using the calibration lines. Yeah, and for comp, we also do density diagnostics, and we can kind of, yeah. Oh, 5 minutes? Oh, probably, yeah. We can, I mean, talk briefly about ice, but I think we'll focus on comp. But yeah, we can also do density measurements so that we measure the density drop along those different structures, and we can kind of calculating the contributions of the photo excitation to the upper energy level of the iron 14 line. And there are different processes in Chianti. Basically, this is the the photo excitation, the radiative decay from the higher energy levels, which is basically collisionally, and the electron collision excitation and the proton collision excitation. So it seems that only at say 1.5 solar radii in the streamer like densities, we will have the photo excitation really dominate the population enter the upper energy level of the iron 14. So it's yeah, so this is what we found with the COM observations. And finally, we also do some comparison with ice. Both ice observations suffer from hot pixels and also SAAs and also data losses. So this is the very small field of view close to the of the quasar region close to the link. We kind of average the spectral lines in those two different regions. One is between 1.035 to 1.06, and the other one is 1.06 to 1.01. And we also measure the line width of these lines. So first, we found there's consistency between the Parmes measurements of the line width in iron 10 and iron 14 in this region. And we don't find a significant evidence for the preferential heating of ions with different charge to mass ratio. And we also do a election temperature and density diagnostics with ice intensity ratios. And I think the election temperature that we measured using the ratios between those EUV lines are kind of similar with the election temperature found by Bimbo. They're using the ratios between iron 11 and iron 14 being visible. And the corona hole observations, we also average the spectra in these three different regions. And due to the poor signal to noise ratio here, and there are less lines that we can observe, but we still have some consistency between the line widths measured by ice and Parmes only in iron 10, because iron 14 might be too hot for the corona hole. But we got some consistency results in these two regions. In the region between those two, the ice line width is kind of affected by some maybe hot pixels, so we don't have a good consistency between those two measurements. And it seems that there are some preferential heating of these ions. If you look at, for example, the effective temperature of iron 8 at the base of the corona hole, it's already 6 million Kelvin here. So just a quick summary, basically, using the data taken during the eclipse, we found, I don't think it's the first, I'm not the first one to found the distinct patterns of the line width variation in the open and closed fields, but we kind of validate that using observations during the eclipse, we can do good measurements of the line widths in the open fields and closed fields. And there are a lot of more opportunities to do the observations during the 2024 eclipse with more observations from the ground and space.
We've got a little bit of time for a question or so. John, you're shaking your head.
No, I'm looking at the 2024 eclipse because Ben's gonna helicopter up there.
I am gonna drive up there.
Okay, that's even better. Fingers crossed.
How, oh, sorry.
Yeah.
I just want to say quickly that in the 2024 eclipse, we should have a much lower instrument line, but
Okay, yeah.
you can maybe use airspace data, or not airspace data.
Okay, yeah, I downloaded our data and tried to make comparison, but
Yeah, it's all dominated by
Yeah.
crazy stuff that was happening with the
How concurrent in time were the comp and the eclipse observations? Was it actually, were you taking during the eclipse or an hour before or after?
I think it's during, because
Okay.
this observation was taken, say, at 17:45 UT,
Okay.
and comp observation started from 17 and ends at maybe 18:15. Yeah.
Let's say